Alright, hello and welcome to the first part of this series where we're going to be discussing, or we're going to be solving for temperature and volume values in a closed water-air system. So first what I have drawn here is a container that contains air and water, and this is an open container, so these arrows up here indicate the fact that the air can leave and come in as it will. And then over here we have a closed container, still containing only air and water. And what we want to find is the final temperature and total volume of the container so that 0.3 moles of water are in the vapor phase. So first let's write out our knowns. And this is going to be the initial phase of this system, and then this is going to be the final. We have 1 kilogram of water. The initial temperature is 298 kelvins, which is about room temperature. And the initial pressure is 1 bar. Then we're also given that the final pressure is 2 bars. And I want to note as well that 1 bar is equal to 100,000 pascals. Okay, so the two equations that we're going to base all of our working things out with is firstly the ideal gas equation, and most people know this one. It's PV equals nRT, and R is our gas constant, N is the number of moles, T is temperature, V is volume, P is pressure. And then we're also going to use partial pressure equation, which is also pretty self-explanatory. Most people know and understand this one as well. So our total pressure, at least in this system, is going to be equal to the partial pressure of water plus the partial pressure of air. So what we're going to do is we're going to rearrange these two equations to be able to solve for final temperature and total volume so that we have 0.3 moles of water in the vapor phase. So we know, we'll start out with the partial pressure equation. And we know that we want this pressure to be equal to 2 bar or 200,000 pascals. Okay, so we're going to find our partial pressure of water from Antoine's equation. And we're going to find our partial pressure of air using the ideal gas equation. So we can sum all of this up as 200,000 pascals is equal to the partial pressure of water, which again we will solve for using Antoine's equation. And the moles of air times gas constant times temperature over the volume of the vapor phase. And again, that's all equal to P total, which is 200,000 pascals. So now we have one of the equations that we're going to use to finish this. Next, let's focus on the specification of the number of moles that we want in the vapor phase. So we know that, let's do number of moles in the vapor phase of water. We want it to be equal to 0.3. And the way that we can solve for this, again, is using the ideal gas equation. So 0.3 is ideally going to be equal to the partial pressure of water times the volume of the vapor phase over the ideal gas constant and temperature. So now we have our two equations. We know R is a constant, it's the ideal gas constant. We know the pressure that we want, 200,000 pascals. We know the amount of moles that we want, 0.3. The number of moles of air can also be solved for and plugged into this equation. Using the ideal gas equation. And since we don't technically know the volume of the vapor phase, we do know that it's the total volume minus the volume of the water. We also don't know the volume of the water, but we know the mass of the water, and we can use density put in this mass and knowing to find the volume. So another thing to note is that the density of water is equal to 1,000 kilograms per meter squared. So now, our only two unknowns are T final and V total. Which we initially talked about here. So what we're going to do using Python is to use these two equations and have these two variables as unknowns and make a code that allows us to solve for the unknowns so that we have 0.3 moles of water in the vapor phase.